So we are almost done with pieces and parts. One of the last pieces that we will look at is something called the detector of the instrument. So again, if I go to the overall picture of our HPLC system and I start taking a look at the pieces and parts, we've talked about the mobile phase tray, we've talked about the degasser, we've talked about the pump now, which is here, and now we're getting ready to talk about the neighboring box, and this is the eyeballs of the instrument, and that is what we call the detector. So we need to talk about this detector. Okay, so what's the story with the detector? Well, we often allude to the detector as the set of eyeballs for the machine. Okay, so the detector is equal to the eyes. This is how the machine sees the components that are coming off of that column, right? So I've got this column, stationary phase, my sample is injected up here at the top, and slowly but surely it goes through the column and out the other end. Okay, well, I'm going to have a set of eyes at the other end that's looking at the things that are coming out and reporting what it sees. Well, the HPLC instruments that are out there can have many different versions, right? There's a number of different versions, so many different detectors. There's tons of them. But what you will be exposed to is only one of these alternate eyeballs that it has or that it can have, and this is called a UV vis detector. So our HPLC system has a UV vis detector on it, and of course the UV part stands for ultraviolet. And the visible part, or the vis, stands for visible. Okay, so when I begin to talk about colors, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. How do you see colors? That's the visible region. When I go maybe to a tanning bed and look at how a tanning bed operates, those bulbs are giving off UV radiation. Something that a light bulb I can see, but UV radiation's typically kind of clear to me in a way. So not really an associated color per se, but it is similar. So UV and visible is how these eyeballs will see the components that's coming off of the column. So that means my hands are tied. Okay, so can I detect any compound that I send into the HPLC? And the answer is no. Right? These are not magic boxes. I can't just put in whatever I want to put in and have it run the sample and have it report data on everything that's in there. That's not how these instruments are set up. They're not that good. So with the UV vis detector, it can only see compounds that absorb light in the UV or the visible region of the spectrum. So not every compound can be picked up. So now this is giving us a problem, because I might have an idea on what I want to do in a laboratory using HPLC, but I have to make sure that that compound is suitable enough to run on an HPLC. So where do I go to find this type of information? How do I know if a compound that I'm interested in measuring or interested in studying is good enough for this instrument because of the set of eyeballs that I have attached to it? Okay, well, let's talk about some properties of compounds for a minute. Number one is that most of the time these compounds have to be organic, not inorganic ones. Organic compounds are things that are mostly made up of carbons and hydrogens. Now, notice what I said, Mostly, not have to. That means there can be other things involved. Oxygen can be in there, nitrogen can be in there, sulfur can be in there. All of those are okay. But on its core, it is a carbon and hydrogen based compound. That's what I want to see the most of. If I start seeing a lot of other things involved, then I begin to question whether this is truly organic or not. And then I begin to question whether this UV vis detector can pick it up. Good news for you is that almost everything is organic. So this is why pharmaceutical companies use UV vis detectors. This is why environmental companies use UV vis detectors. Because almost everything that comes my way, everything that I'm exposed to on a daily basis, everything that's important really, does have some UV vis affinity, meaning it can be seen by this particular detector. Now, not all organics are going to be able to be measured. So what are some of the properties of the organics that allow it to be really good candidates for this type of detection system? Well, number two is that these compounds are really wanting to be preferred in rings. Okay, so if I draw the structure of benzene, benzene is a very carcinogenic substance. And benzene looks something like this. It is a ring structure. That ring structure is a dead giveaway that this can be picked up by UV vis detection. So if you're starting to look at molecules and you look at their structures and they have these ring systems in place, then that would be okay to run on a UV vis detection system versus something that looks like this, right? So there's no ring system that's here. So if I put this into a column and allow it to travel through the column and allow it to come out the other end, this eyeball does not see that molecule because it doesn't absorb UV visible light. However, if I take something like benzene and I put benzene into the HPLC system and allow it to separate, out of the other end, this UV vis detector will be able to take a look at this molecule because it is a ring system and it can absorb UV light, and the instrument can tell me some data on that. It records it as something that it sees when it comes out of the other end. So ring systems are good when you want to analyze things on a UV vis detector. The third thing is what we call a conjugated system. Conjugated system. Okay, so if I go back up to this example and I take a look at this molecule, there's no ring involved, so that's not going to be seen. But if this straight chain molecule had a conjugated system, meaning double bond, single bond, double bond, double single double, DSD is what we look for, double single double, and it can continue on if it wants to, double single double single double, but as long as it alternates back and forth that way, we call that a conjugated system, and that conjugated system will be able to be picked up with the UV vis instrument, and I will be able to measure that as well. A lot of times the conjugated systems are colored. So if you take a look at beta carotene and you take a look at that structure, or lycopene and you take a look at that structure, those are conjugated systems, and those show up color when I view them with my own eyeballs. They're oranges and reds and yellows. So conjugated systems and ring systems do extremely well when it concerns UV vis detection. So let's take a look at some examples. So this is our first example, and this is beta carotene. And if you look at the structure of beta carotene, you're going to see a ring that is here and a ring that is there. All right, so that's already kind of a dead giveaway that this molecule would absorb light in the UV vis area. But on top of that, this is a very good example of what we call a conjugated system. It goes double, single, double, single, double, single, double, single, double, single, and on and on and on and on and on. So this is a conjugated, heavily one of the most conjugated double systems that we know of beta carotene, and it forms a very good candidate to be able to be detected by UV vis detection. Here's a molecule that we call caffeine. So if you're drinking your soda or if you're drinking your coffee in the morning, you are drinking this caffeine molecule. And this caffeine does really well under UV vis absorbance. And you know that it's going to do really well because, again, you see some ring systems that are involved. So here is a ring system, here is a ring system, and because of that, this does pick up UV visible radiation when it's bombarded by this light beam. It sucks it up. And then finally, here's another example. This is the molecule for aspirin. Aspirin does extremely well on the HPLC instrument. You can shoot aspirin onto the instrument. It comes out beautifully. That's because the eyeballs can see it leave the column. And it can see it because this structure has a ring involved. So once again, I see a ring that is here, and that ring is a dead giveaway. It probably absorbs UV light or visible light, and I'm able to shoot that onto our HPLC instrument and measure the amount or quantity of aspirin that I have in a sample. So that's the story with the detector. So again, mobile phase tray up at the top, then it's the degasser that's down here below, then it's the pump that pulls everything into the instrument, and then over here to the right hand side, that is my detector unit. Okay? So if I go through and take a closer look at the detector, here it is. This is with the front closed and the front open. And if you notice, it looks very similar to the pump in a way. So up here is with the face closed, down here is the face is open, and I see something that looks like a pump, but it's not. We call this a flow cell. The reason we call it a flow cell is because this detector is getting sample. You can kind of see that right there to the left-hand side. The sample is leaving it, and it's coming into the detector. When it comes into the detector, well, there's a flow path that it follows, and that's why we call it a flow cell. And it goes through the detector and out of the back of the instrument into a drainage. So that's the detector that's opened and closed. Here's a closer value, or a closer, not value, but a picture of what the detector box looks like. Notice up here at the top it says SPD20A. So that detector, that's the model number that we have used. And this has a couple of buttons on it called 0 and run and mark and VP and sleep. Really, we don't touch anything at all on this box. We never really mess with it. The software takes care of that itself. But if I was messing with the front of the box, the only thing that I would mess with the most would be the 0 button. I want to make sure that these things are teared out just like your balances when you begin to use them. The detector with the cover open, this is what it looks like. It might be a little fuzzy, but you're seeing some sample introduction and you're seeing the pathway of the sample leaving. So this box right here is the UV vis detector. It's very, very tiny. There's a small chamber on the inside that starts sucking sample out and analyzing that sample before it spits it out into the waste jug that we'll see a little bit earlier on or later on. The light spectrum, let's take a look at that for a minute since we've brought that up. We said that UV and visible, that's the only working ranges that we are allowed to look at. Well, the visible represents a very small area of the light spectrum itself, right? It's not very, look at how tiny that sliver is. So this is where we see all of our colors. The UV vis detector will be looking through all of those colors as well: red, orange, yellow, green, blue, indigo, violet. But it also goes into the UV region. Ultraviolet, ultra means above. So above violet. It scans this area as well. So all of the other light spectrum areas it doesn't touch. That's the purpose of some of our other instrumentation that's in our laboratory. We do not go through X-ray. We do not talk about gamma. We don't go through infrared. We don't go through radar. We don't go through FM or TV or radio waves or any of that either. So that's the purpose of some of our other equipment in the laboratory. Some of our other instruments will focus on different parts of this light region to measure samples and to provide us some data from those sample preps that we do in a lab maybe on a daily basis. So that's why we have so many different versions of equipment. And then even with HPLC, we said that a UV vis detector is only one detector that can be hooked up to this instrument. So some of the other detectors that we can hook up play off of these other areas of the light spectrum. So again, depending on what I'm analyzing, I've got to make sure that I've got the right ingredients to make sure that the instrument is doing its job the proper way. And the detector is one of those ingredients that I want to double check before I go shopping. So again, ideal candidates are kind of here for you. Colored solutions work really well because that's your visible region. And then caffeine and aspirin at the same time. We talked about why those are good candidates. We often see a number associated with them. 273, 254. These numbers are coming from a reference manual, either the Merck or the CRC. That's actually so important, I'm going to write it down. So Merck or the CRC. Merck is a reference manual, just like the CRC is a reference manual. And these give physical and chemical data from all of these compounds that might be coming out of my studies or out of my research or out of the lab that I'm doing or some kind of experiment that I'm doing. It gives me a way, a reference book, kind of like Wikipedia, that I can go to, open up, look at aspirin, and it will tell me certain things about that compound that I need to know if I want to analyze it. And one of those values that it tells me is this thing called a lambda max, maximum absorbance. So this tells me that in the UV vis region, this molecule, if it's caffeine, does extremely well at 273 nanometers. That means out of that region, that is the one number that I can pull out that I can do some studies on. The same thing is going to happen with aspirin. Out of the UV vis region, aspirin absorbs really well at 1 wavelength, or 1 lambda max, or 1 nanometer. They all talk about the same thing, you know, tomato, tomato, it's what you want to call it. And 254 is the number that aspirin behaves really well in, and that's in the UV vis region, just like caffeine is. It's in the UV vis region. So this is a number that often is given to me. It's telling me, take your instrument, dial in to this value, and when you take a look at this value, this is where this molecule in particular will absorb really well. So here, caffeine and aspirin are absorbing at different wavelengths, and I want to make sure that if I'm analyzing for caffeine, I dial the machine in to 273. If I'm analyzing for aspirin, I'll dial the machine in to 254. If I'm analyzing for something else, that might have a different wavelength that I need to dial into. But this is a number that is required, and it is reported most of the time when you do your studies. So this is the story, overall picture of a detector. It gives us our limitations. It tells me what I can pick up and what I cannot, what I can see and what it cannot see. So in the next video, we'll finish this up and we'll talk about the waste jug.